Alright, so what we're going to do now is going to talk about electric fields. And electric field is a second field you're going to learn about. So there are all total three fields that we learn in your A levels: gravitational, electric, and magnetic field. So it is a field of force. So that means it is a region where an object will experience a force. So what kind of object will experience a force in an electric field? It must be a charge. So the definition of electric field is a region where an electric force is experienced by an electric charge. Now, how do we draw electric field lines? Now, when we were doing gravitational fields, I also explained to you that when you draw the direction of the fields, it must follow a certain sign convention. For gravitational fields, what do we use to determine the direction of the field lines? We use the direction of the force acting on a test mass, not positive, I just test mass. So meaning to say, if I put any test mass here, it will be attracted. Right? The force is attracted, so therefore the field lines will follow the same direction. Then, when we are doing AS also, we actually learn a little bit of how to draw electric field lines. So it also has a certain sign convention. So the direction of the electric field lines follow the direction of the force acting on a positive test charge. So meaning to say, if let's say this charge here, this positive charge is the one I want to draw the electric fields for. So I want to draw the electric field for this positive charge. I put any positive test charge, all these positive test charge will be repelled. So all the lines must be outwards then. If I want to draw the electric field for a negative charge, then I will put positive test charge also everywhere, and all the positive test charge will be attracted. Therefore, all the lines are inwards. So always remember, the direction of the electric field lines will be in the direction of the force acting on a positive test charge. So that means even if they didn't draw which is positive, which is negative plate, or they didn't draw what are the charges that produces a field, as long as you see an electric field, you put a positive test charge, the positive test charge will experience a force in that direction. But you put a negative charge, then what happens? You will experience a force opposite the direction of the field. So this is what you must remember. And as in all field theories, if the lines are close together, means near to the charge here, the lines are closer, means the field is stronger. Further apart, as you go away, the lines get further apart, that means it's getting weaker. Okay, so why do you have electric field lines? It's because of the forces between charges. And the forces between charges is given by Coulomb's law. And the good news is, if you have remembered Newton's law of gravitation for masses, you can also remember Coulomb's law of force for charges, because they're actually quite similar. Remember, Newton's law of gravitation says every mass attracts any other mass, right? But in electric fields, you cannot use that, because your charges not only will attract, but they can also repel. Example, right? For like charges, they will repel. Opposite charges will attract. So we substitute the Newton's law of gravitation, like every mass will attract any other mass, with the force between 2 point charges. Now, after that is very similar, because Newton's law continues saying is directly proportional to the product of the masses. So here we say is directly proportional to the product of their charges. And then Newton's law says, and is inversely proportional to the square of the distance apart. Coulomb's law exactly the same, inversely proportional to the square of the distance apart. So if you remember one, you remember the other. So therefore, why are they the same? Because Newton's law is the formula for point masses, whereas Coulomb's law is for point charges. So you must always take the entire charge to behave as a point charge at the center. So all the distances that we're going to see must be measured from center of charge to center of charge. Okay? So if we were to write down in an equation, so you will notice that F will be proportional to product of two charges, and then you will inversely proportional square of the distance apart. So you combine, you get K Q1 Q2 over R squared. So what is the K here, which is a constant? So the K here is actually your 1 over 4 pi epsilon naught. So the whole thing, 1 over 4 pi epsilon naught, is your constant. So what is this epsilon naught? Now epsilon by itself is just permittivity. Epsilon naught is permittivity of free space. Free space is vacuum. So what does it mean by permittivity of free space? It means permittivity of vacuum. Now, permittivity is like a measure of how easy or how difficult the electric fields can pass through a certain region. Now, there are certain mediums where the electric field can pass through easily. Certain mediums where the electric field will find it very hard to pass through. So in the mediums where it can pass through easily, the force between the charges will be strong. In the medium where it cannot pass through easily, then the force between the charges will be weak. Now, we may not be able to imagine it for electric fields, but it is something similar to your magnetic fields. For example, let's say you put two magnets near each other. If you leave it in air, then there will be a certain force between them. But if let's say you put a piece of wood in between, then you find that the force becomes weaker. But you put a piece of metal between them, the force becomes stronger. So that is that is an example for magnetic fields, and that property, how easy or how difficult the magnetic fields can pass through a region, is called permeability. So but we'll learn that later, but electric field, same concept, but we call it permittivity. So if you look at the formula here, what do you think? How does the permittivity affect the field? Higher permittivity easier to pass through, or lower permittivity easier to pass through? Now, some people think because of the word permittivity, that means permit means easier to pass through. Actually, so they think higher permittivity easier to pass through, but it's wrong. Higher the permittivity, the harder to pass through, because if you were to substitute into this equation, you get F equals to 1 over 4 pi epsilon naught Q over R squared, right now. So the higher the epsilon naught, the lower the force. Not like epsilon naught. Higher the epsilon, the lower the force. So therefore, higher permittivity means harder to pass through. So permittivity of free space is epsilon, that means permittivity of vacuum. It is given in your data booklet as 8.85 times 10 to the power negative 12. I'll give you an example. What do you think is easier to pass through, air or vacuum? Vacuum is easier, right now. So in air, the permittivity is slightly bigger because it's slightly harder to pass through. For example, the permittivity of air is about 1.00005 of the permittive vacuum. It's slightly bigger. So you can treat it to be the same. And what about water? And then in water, the permittivity is 80 times the permittivity of vacuum. So that means it's 80 times harder to pass through. The force will be 80 times weaker. Example, right? You talk about table salt, right? Which is chemical composition is sodium chloride, right now. So sodium ions and the chloride ions will be attracted to each other. In air, the force is significantly large enough such that it can form crystals. But once you put it in water, remember the water permittivity is 80 times greater, so the force is 80 times weaker. So what will happen is they cannot hold, so they'll dissolve. That's why salt dissolves in water. Alright, so this is an example of how permittivity works. So then the next question is, if one of the charges is positive and one of the charges is negative, so do we substitute the positive and negative inside there? Because it will make a difference, right? Not if one is positive, one is negative, when you multiply you get negative, but if both positive and both negative you get a positive, right? Now, so should we include the positive and negative into the charges? Now for all vector quantities, you don't have to put any positive and negative. You just drop the positive or you drop the negative from the calculation. You know why? Because for vector quantities, a negative force, it doesn't necessarily indicate a particular direction. For example, let's say you have a force of negative 5 newtons. So, but it doesn't tell you whether it's the right or left or up or down or front or back, unless you have a sign convention. So what you would do to make your life simpler is to drop the negative, and if they one direction, then you just state left or right or up or down. Because in some of the books that you see, textbooks, you will notice that there's a negative there. So that is actually for gravitational field. So I will explain before, in gravitational field why they put negative is because for gravitational fields, negative indicates that they're always attractive forces, because in field theory negative force is attractive but positive is repulsive, but we don't really use that, so we can just forget about it, just drop all the negative. So okay, now we're going to talk about what is electric field strength. So electric field strength talks about how strong the field is, right? So the definition of electric field strength, you have actually learned it in your AS itself. Remember the definition of electric field strength is force acting per unit positive charge. So why is there a positive charge there? It's because field strength is vector or scalar. It is vector because electric field strength follows a particular direction. So what's the direction that electric field strength follows? It follows a direction acting on a positive test charge as well. The force acting on a positive test charge. So just now, remember we use a positive test charge to determine direction of electric field. That is the same way we determine direction of electric field strength, because electric field strength is also a vector. Now, electric field strength, the formula or the definition is F over Q right now. But if I were to substitute the force into here, so Q over 4 pi epsilon naught R squared, if I were to substitute inside here, you notice the small q will cancel, so you're only left with 1q at the end. So this is the formula for electric field strength. So the question is, when do we use this formula and when do you use this formula? What is the difference right now? Now, this formula has only 1q. This formula has also only 1q. So which q do we use? Right? Similar to your gravitational field. Remember, for gravitational fields, if the m is at the bottom, is a test mass. M on top is the mass that produces a field. So for electric field, same thing. If the q is at the bottom, it is the less important charge. So this will be a test charge. If the q is on top, it is the more important charge. So it's the charge that produces the field. Example, if let's say you had a lithium ion, okay, lithium ion, and you have electric fields around them, around this nucleus. Alright, let me just draw the lines, this one. So what will happen is, if let's say I wanted to find the electric field at a point, let's say at here. So what I must do is I must put a positive test charge here. So the positive test charge will be repelled, right? So that means the field strength at this point A is also to the right. So the field strength follows the direction of the force acting on the positive test charge. Now, if let's say the positive test charge here is a proton, so the field strength of the lithium ion at point A will be the force acting on the proton divided by the test charge, which is the charge of the proton. If I want to use this formula. But if I want to use this formula, then this Q will be the charge of the lithium ion. So it's the charge that produces the field.